Welcome back, pre-calc students. We are still making our way through section 9.1. We are on day 2 of section 9.1. Quite a bit to cover in this day 2 portion, including how to represent finding the sum of a sequence. That's part of our essential question there. And we'll look at some of the objectives, including factorial notation, summation notation, how do you find the sum of the series, and we'll see if we can get into some real life problems. This may end up being more than one video, but we'll play it by ear. Let's see how things go and how lengthy things get. So let us get started. We are in your note-taking guide. We are actually not in your note-taking guide to begin with. We will get back to your note-taking guide. We should be in your extra example packet right after example 5, so it should be on the back side. Looking at recursive definition for sequences. This is not defined in your note-taking guide, so that's why we've added it a little bit in this direction. We actually practiced this with our ACT packet recently as well. So some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms, and then all of the terms of the sequence are actually defined by using these previously defined terms. So it's a good definition, but it seems rather wordy, so let's actually practice a few examples. So example 6 and example 7 are two great examples of recursive sequences. So they want the first 5 terms in example 6 of the sequence defined recursively as a sub 1 equals 3, so we actually know the first term, and a sub k, you can also call it like a sub n, is equal to 2 times a sub k minus 1 plus 1. So what this is saying, to get the kth term, take the term that comes right before it, that's the a sub k minus 1, multiply it by 2 and add on 1, and this is only good for k values that are at least equal to 2. Well, that makes sense because we were already given the first term. We just need to find the second, the third. We'll move the fourth and the fifth over here. See if we can conquer this problem. So to find the second term, I'm going to take 2 times the term that comes before it, which would be the first term. I'm then going to add on 1. Okay, so the first term was equal to 3, so we're going to take 2 times 3 plus 1, and we get the second term to be 7. To find the third term, bump this up just a bit, you're going to take 2 times the term that comes before it, which is the second term, and add on 1. The second term we just calculated to be 7, so 2 times 7 plus 1 gives us a third term of 15. Okay, if we keep that pattern going, to get the fourth term, 2 times the third term plus 1, so 2 times 15 plus 1 should give us 31. And finally, to get the fifth term, 2 times the fourth term plus 1. So 2 times 31 plus 1. So we have 62 plus 1 gives us a nice 63. Now, see if you're getting comfortable with that. That's a recursive definition. ACTs really like recursive formulas, so it's good things to practice. Now we have Fibonacci sequence, and Fibonacci sequence is only defined recursively. They give us the 0 term being 1, the first term being 1, and they say, hey, if you want the kth term, any term that you want there, you're going to take the term that came 2 before it, add on the term that came right before it, and that will give you the next term. That will give you the kth term. So we want the first 6 terms. So if we're finding the first 6 terms, we actually can count a sub 0 as the very first, a sub 1 as the second. So we'll call that the third, the fourth. Whoops, let's actually write my subscripts are getting messed up. Okay, and one more. How about we'll call it the fifth? So a sub 5. That should give us the first 6 terms. 1 and 1 are the first 2 terms. We already have those. So according to the definition, you take the term that comes 2 before the term you're looking for, add on the term that came right before you're looking, or what you're looking for, and that should give you the next term. So I'm just going to add a 1 and a 1 together to get 2. To get the third term, take the first term and the second term, add them together. First term was 1, second term was 2. We get a grand total of 3. To get the fourth term, a sub 4, take the the second term, add on the third term. So you get to take 2 plus 3 and end up with a 5. And finally, for my very last term, I'm going to take the a sub 3, you might call the third term, add on the fourth term. Third term is 3. We'll add on 5 to that, and we get a value of 8. So we have the list of terms being 1, 1, 2, 3, 5, 8. And I think that answers example number 7. Nicely done. Okay, now we get to go back under Roman numeral number 2 in your note-taking guide. And under Roman numeral number 2 in your note-taking guide, we start out with factorial notation. So some very important sequences in mathematics involve terms that are defined with a special symbol that represents a special type of product called factorials. The definition for factorials that we can start plugging in or writing down: if n is a positive integer, then n factorial is defined as, and this is what you want to write down, n factorial. So n exclamation point equals 1 times 2 times 3 times 4 times ... times n minus 1 times n. So all integers from n down to 1 get multiplied together to give you n factorial. And the special case that you just need to keep in mind, just need to memorize, that 0 factorial actually is equal to 1. Okay, let's look at example 8, and that's back into your extra example packet. So finding example 8, it's actually, let's see if we can find it here. There we go. So write the first 5 terms of the sequence defined as a sub n equals n to the second divided by n factorial. So you're going to begin with n equaling 0, and if I want the first 5 terms, we're going to do a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4. There we go. That should give us our first 5 terms. So 0 through 4 get plugged in for n. So we get 2 to the 0 power divided by 0 factorial. And we already know that 0 factorial is a 1. 2 to the 0 power is also a 1, so we end up with a 1 for the first term. To get a sub 1, you're going to replace every n with a 1. So 2 to the first over 1 factorial. That gives us 2 over 1, which is just a 2. And to find the a sub 2, you're going to replace each n with a 2. So 2 squared over 2 factorial. 2 squared is 4. 2 factorial, 2 times 1 is 2. That simplifies down to a 2. We're making it here. The next substitution we're going to make for n is a 3. So it's 2 to the third over 3 factorial. 2 to the third is 8. 3 factorial, 3 times 2 times 1 is 6. 8 over 6 simplifies down to 4/3. And a sub 4. So replacing every n with a 4. We get a to the 4th over 4 factorial. 2 to the 4th is 16. 4 factorial, 4 times 3 times 2 times 1 should give us 24. And 16 over 24, they both divide by 8, so we get 2/3 out of that. And that should take care of what we need to calculate for that problem. Okay, so that's some work with factorials. Let's see what we can move forward to. Ooh, we get to go to the back side of your note-taking guide, so page 156, and we get to continue with example 2. And example 2 is really what you see for part B, but in order to understand part B, I think we need to kind of pull apart the pieces in part A. So let's add part A into your note-taking guide. And let's just understand how I can rewrite this and decipher and try to simplify things. So I'm going to start up in the numerator with that 8 factorial. Now I know literally with the numbers you could just punch it all into your calculator, but that won't help you with the part B. So let's actually rewrite the numerator as 8 times 7. I like to do a descending order when I do factorials. So something to this effect. Does that look like that represents 8 factorial? 2 factorial and 6 factorial. Let's see if I can get everything written out here and not skip any numbers. I don't want to skip any numbers. Okay, cancel out as much as you can between the top and the bottom. Look at this, 8, or for 6 factorials, I can cancel out these 6, 5, 4, 3, 2, 1s. I don't really need that 1 in the denominator. And I can simplify the 8 down to a 4, and the 2 can simplify down to a 1. Or be crossed out. And what we're left with, we have a 4 times 7, which is 28. And just a 1 in the denominator, so we can just call this 28. And that might have been quicker than putting it into your calculator. But it actually does help us in Part B, which is why I wanted us to do the Part A. Part B, I can't possibly write out all of what n factorial represents, but I do understand that it means n times n minus 1 times n minus 2 times n minus 3, all the way down to times 2 times 1. All of that. The denominator, if it's n plus 1 factorial, that starts with n plus 1. Decrease that by 1, that gives you n. Decrease that by 1, n minus 1, n minus 2, n minus 3, down to 2 times 1. So, just like I did in Part A where I crossed out a whole bunch of information, I get to cross out a whole bunch of information in Part B. See if you can start crossing things out. What do I get to cross out? I get to cross out n, n minus 1, n minus 2, n minus 3, and everything else that's further to the right. I've canceled out everything from the top. I'm left with just a placeholder of 1 on the top. Down in the denominator, I'm left with the factor n plus 1. And you simplified that term. That's it. That's your answer to Part B. Okay, we're going to move into Roman numeral number 3 and see if I can get Roman numeral number 3 done in this video. In Roman numeral number 3 in your note-taking guide, we are looking at summation notation or sigma notation, a convenient notation for the sum of the terms of finite sequence. It's called summation notation or sigma notation. It involves the use of uppercase Greek letter sigma, and that's that quirky little symbol that you see going along with the definition right in the middle of the page. So the definition of summation notation or sigma notation, the sum of the first n terms of a sequence is represented by this sigma notation. I'm right in the middle of the page here. I equals 1 to n of a sub I. So what that represents, if we expand that, that represents, and this is the first thing that you write down in your paper under Roman numeral number 3, it represents a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. So since I started at 1, that's why our first term is a sub 1. Since it stops at n, that top value is n, that's why our last term is a sub n. The I variable represents your index of summation. Yep, and we get to write that down. So it's called the index of summation, that variable right there. You can change it. It doesn't have to be an I, but I seems to be a very reasonable letter that we use there, a variable that we use there. N, that top number, is called the upper limit of summation. And 1 is called the lower limit of summation. There's space for all three of those terms. Now, something else that I would add that we're going to be spending a little bit of time with that's not officially in your notes, and there should be some space off to the right. You can call them properties of sums. So you can pause the video, write these down. Properties of sums. If it's just a constant following sigma notation, that sum is just going to be that constant times the upper limit of summation. C times n is going to be the value of that sum. If you have a constant, I'm looking at property 2, if you have a constant being multiplied by a sub I, that constant can get pulled out in front. It's not necessarily needs to stay a part of the summation. You can just multiply the sum at the end by c and you'll get the same answer. And then 3 and 4, those properties come together. The only difference between property 3 and property 4 is the adding versus the subtracting. If you are adding between two pieces within the summation notation, you can separate into two different summation notations, and exactly the same idea with subtraction notation. So get that copied down in your note-taking guide, and I'm going to see if I can run through one last slide before we call it quits on day 2, part 1. Okay, so what I'm doing in example 3, in this example 3, is right in your note-taking guide, we're adding on a few parts, so if you can squeeze these parts in or put a little post-it in your note-taking guide, that would be great. This really does represent your part A. So part A is exactly what was written in example 3. What this tells me is that the first number I'm going to plug in for I is 2, and then I'm going to continue to plug numbers in, integer values in, until I get to plugging in a 7. So this is what it's going to look like. I'm going to start by replacing I with the 2. I'm going to use parentheses just to help us out here. So that's what I get for my first term. Add on, let's plug in a 3 for I. That's the next integer after 2. Add on, plugging in a 4 for I. Add on, plugging in a 5 for I. Add on, plugging in a 6 for I. And finally, let's add on, plugging in a 7 for I. I get to stop there because 7 is the top number. And when you look at those calculations, you look at plugging those numbers, the 2, the 3, the 4, the 5, the 6, and the 7 in, you should end up with a total of 8, added on to 11, added on to 14, and then 17, 20 for the second to the last term, and the last term being 23. So we should end up with a grand total of 93 for that sum. Okay. For part B, I don't have as many terms to find because I get to start at the k value of 3. I get to start by substituting 3 in, and I stop as soon as I plug in a 6. So you're going to look at 1 plus 3 squared. Add on to that 1 plus 4 squared. Add on to that 1 plus 5 squared. Add on to that 1 plus 6 squared. Whoops. There we go. That's what it will look like. Okay, so I get 10 added to 17, added to 26, added to 37. And if we start adding this calculation I don't have off the top of my head, you would think it'd be somewhere in here, but 27 plus 26 is going to give us 53. 53 plus 37, so this is our 53, plus 37 should give us a total of 90. So 90 would be our sum. Now, this would be a great time to pause the video, see if you can get through part C. Try it on your own. I'm going to write the terms down, and then I'm going to actually pause the video so that I can make the calculation on this. But remember, you're going to start with an I value of 0 and work your way up to an I value of 8. See if you can write it out. Writing it out is what we call expanded form. And we have to use every integer from 0 to 8. This may not be a very pretty answer in the end, but at least to put it in an expanded form would be great practice. So there is my expanded form. I'm going to pause to get the answer. It might be just an ugly decimal, and we'll be okay with that. I'll be right back. Okay, so the answer I'm coming up with, at least an approximation, for part C, 2.7183. See if you can come up with that same approximation. And we can come back with questions on things. We still have another 3 slides, and I'm going to continue that as another video, but not that much left. We've gotten through a lot with sigma notation and recursive formulas. So good luck with your assignment. Please come back and listen to section 9.1, day 2 continued. Thanks. Bye.